I'm an astronomer, and I'm going to talk about something beyond the Earth, namely the most complex system we know about, which is the universe. And I'll spend the first half of my talk discussing things beyond the Earth, but my main theme towards the end is going to be that the most complicated things in the universe are right here, human beings and their societies. So I'll focus in the second half of my talk on some issues which I have written about concerning the present century and the problems we confront. But let's start off by thinking about what lies beyond. And I always enjoy talking about this because we should think of cosmology as an environmental science. The night sky shown there is the one feature of our environment that's been shared by all human beings throughout all history. They've all stared up at the sky and wondered at it. So it's not surprising that it fascinates a wide public. And although this isn't a sermon, I am going to start with a text. The text is the famous closing words from Darwin's Origin of Species. Whilst this planet has been cycling on according to the fixed law of gravity, from so simple a beginning, forms most wonderful, have been and are being evolved. Well, Darwin's simple beginning is the young Earth, which is already quite complicated. It consists of complex geology, complex chemistry, etc. And if I were to describe in one sentence what cosmologists are trying to do, it's to go back before Darwin's simple beginning, to understand where the Earth came from, why the atoms in it exist in the proportions they do, why the stars exist, indeed why anything exists, and is there an emergence from a simple beginning of the universe to Darwin's simple beginning, and how can we trace that out? So that's going to be the theme of the first half of my talk this afternoon. Well, let's start off with what we've learned about our universe via cosmic exploration. I'm going to give you a sort of quick tour of the universe from what we've learned. But bearing in mind that I'm going to focus in at the end on the Earth, which is indeed the site of the greatest complexity we know about. Well, being a Brit, I'm going to start off with Isaac Newton, probably the greatest British scientist. I show him especially because he came from the same college where I now am, and incidentally, that view would have been exactly the same in Newton's time as it is now. The inmates of the college have changed, but the view hasn't changed. And I like to say that Trinity has been in decline for 300 years since we haven't had anyone as good as Newton since then. But Newton was probably one of the first people to think about space travel. He was, of course, in contrast to Darwin, a great unifier. He showed that the force that holds the planets and the moon in their orbit is the same that holds us to the ground and makes the apple fall. So he was a unifier, in contrast to Darwin. He was also, in contrast to Darwin, a most unpleasant man, solitary and reclusive when young, vain and vindictive in his old age. But nonetheless, we have to admire his achievements. And I like to show this picture, which is from the English edition of his great book, The Principia, because I think it's still the nicest way to explain the concept of orbital flight. What's happening is that cannon balls are being fired from a mountaintop, and you can see if they're fired fast enough, then they curve downwards in their trajectory no more steeply than the Earth curves away underneath them. They go into orbit. And Newton calculated that to go into orbit, you've got to fire your cannonball at 18,000 miles an hour, far beyond what was possible for the cannon of that time. And as we know, it wasn't until 1957 that the Soviet Sputnik was the first object to achieve orbital flight. And then there was an exceedingly rapid technical development. 4 years later, Yuri Gagarin went into space, and 4 years after that, we had this iconic picture taken by astronauts orbiting the moon. And in 1969, we had Neil Armstrong's first small step on the surface of the moon. And I treasure this picture signed for me just a few years ago by 7 of the Apollo astronauts. Now, it's perhaps interesting for those interested in technology that the last men on the moon returned in 1972. So you've got to be middle-aged to remember when men walked on the moon. I like to tell my students that they know that the Egyptians built pyramids, they know the Americans landed men on the moon, but these both seem ancient history motivated by strange national goals. And indeed, as we know, the imperative was to beat the Russians to the moon, and after that, the effort in manned spaceflight languished. Otherwise, there would have been footprints on Mars long before today. But many people have circled the Earth, many in the space station like this, and many of you may have already seen the film Gravity, showing what could happen if you're not too careful there. Men have been no further than low Earth orbit. But unmanned spaceflight has proceeded apace, and not only has it been crucial technologically for sat-nav, weather forecasting and communications, but it's also been important in exploring all the major bodies of our solar system. And I'm going to just show you a few pictures of that. So if you were on a trip out towards the outer planets, then if you look back at the Earth from about 5 million miles away, you would see a picture like this. This shows a half Earth and a half moon. The sun is coming from the right. And you might on the way pass asteroids like this, which could be dangerous if they get too close to the Earth. But you then get to the red planet, Mars, and many spacecraft have orbited Mars and landed on Mars. And let me show you a few pictures. This is a picture taken by a European satellite of Mars. This is a big gorge on Mars, several miles deep. And 18 months ago, the American Curiosity probe, which is about the size of a car, landed on Mars and is trundling around the surface. It landed where that ellipse is in the top left of the huge crater, and it's been trundling around ever since, and it'll go on for 10 years, and it'll eventually climb that mountain in the middle of the crater, which is actually several miles high. And this is a view it took. You can imagine standing there. It's about as high as a person, so if you were standing on Mars, this is the sort of view you would see. And this is interesting. This is a picture taken from a satellite orbiting Mars, and if you look carefully, you can see little tracks along the bottom there, and those are the tracks made in the first 2 months by the Curiosity probe trundling over Mars. And it's now traveled, I think, 30 kilometers altogether, and it's taking geological samples all the way. Not quite as well as a geologist with his hammer, but doing a pretty good job in understanding Mars. And here's another image which it's taken already, and you can see the geological strata, and as it climbs these hills, it will sample the geology of Mars very carefully. Well, going beyond Mars, the next planet is Jupiter. Here it is, the giant planet of the solar system, and that shows one of its moons there, and it's got the 4 famous moons which were found by Galileo in 1611 with his first telescope, and these have all been observed close up, and they're very different. This is Io, which is sulfurous and volcanic. This is Europa, which is covered in ice. There's probably an ocean underneath the ice of Europa. And this is a close-up of the ice, indicating that it's had a sort of complicated history. So the moons of Jupiter, which are going to be probed by future spacecraft, are very different, and of course one wonders what might be swimming around under the ice of Europa. Oh dear. Sorry. The slides are... When did that happen? Just now? Okay, so okay, so I'm not yep, yeah. Thank you very much. Yes. This is a close-up of the ice on Europa, and as I said, there may be something swimming around underneath it. This is Saturn, which has the rings, and this shows the rings edge on. And I'd like to show this picture. This is a rather beautiful picture. This shows an eclipse of the Sun by Saturn. A spacecraft called Cassini, which is even now still orbiting around Saturn, looking at its moons, in this picture is beyond Saturn at such a distance that the Saturn just blocks out the Sun. So it's a total eclipse of the Sun by Saturn, and the rings of Saturn are still in view. And the Earth is where the little dot is. You can't quite see it in this picture, but because we are now a very long way from the Earth, it would take several hours for a radio signal to get from here to there. I just wanted to mention a great feat of robotics. The Cassini probe carried in its cargo bay a European robotic probe called Huygens, which was supposed to land on Titan. Titan is a giant moon of Saturn. And it was supposed to do this. Titan was known to have an atmosphere, and it was supposed to open a parachute and land on the surface. And of course, it's not being controlled from Earth. This robot was on its own because it's several hours travel distance. So it was released, and it was supposed to do that. And indeed it did. The pictures on the left and the center were taken on the way down, and the right-hand picture is where it landed. Now, this may look a rather nice place, rivers and a little lake, but the rivers are liquid methane, and the temperature is minus 160 degrees centigrade. So it's a very cold place. Well, I expect that in coming decades, robotic probes will bring back details of all the major bodies of the solar system, the planets and all their moons. But are humans going to go back there? This is a picture of Harrison Schmitt. He was one of the last two men on the moon, and in this moon buggy he went around collecting moon samples. So the question is, will people go back to the moon? I don't want to spend too much time on this. I personally think that the future of manned space flight lies not in NASA-type projects where you've got to be very concerned about safety since you're sending civilians, but I think it's going to be cut-price flights by enthusiasts. The private space program is starting, especially in America, and there will be people prepared to take much higher risks than NASA could impose on its astronauts, and the first people to go into space that way will perhaps go to Mars with one-way tickets. But just in case anyone's interested and got the money, you can go into low Earth orbit. Of course, people have done that. But the next thing will be a voyage round the backside of the moon, which will take about 5 days and take you further from Earth than any human beings have gone. That will take about 5 days, cost you $150 million. And I gather there are tickets sold for the second flight, but not for the first flight. And maybe that tells you something. It's also possible to go to Mars, either a one-way ticket and land, or to go round the back of Mars and come back again. That would take about 500 days and be a rather boring trip. And so the ideal crew there is a stable middle-aged couple that don't mind being cooped up together for 500 days and are beyond reproductive age, so the radiation damage which they might get from solar flares doesn't worry them too much. So I think people will go into space, and I think probably by the end of a century, there will be communities living away from the Earth on Mars or in asteroids. And of course, that's a very alien environment, so whatever constraints we impose here on Earth, I think we'd wish those people good luck in using all the techniques of robotic of robots, genetic modification, and silicon implants to adapt their descendants to live in that very alien environment. So within a few centuries, the post-human era will begin, because they will evolve very differently from the species that's adapted here on Earth. But this, of course, begs the important question, is there life out there already? And I think, despite what I've said about possible life under the ice of Europa, most people are pessimistic about anything other than very simple life elsewhere in our solar system. The Earth is uniquely well adapted for life. But the interest in alien life has been hugely boosted by a very important advance in astronomy in the last decade or two, which is my next topic. And this is the realization that the night sky is much more interesting than it used to be thought to be. We now know that most of those stars, the stars you see in the sky every clear night, are not just twinkling points of light. They're in most cases orbited by a retinue of planets, just like the Sun is orbited by the Earth and the other familiar planets. How do we know this? Well, there are two techniques, both very simple in principle, so I'll mention them. Neither involves directly measuring the planet or observing the planet. Both involve looking for the effect of a planet on the parent star it's orbiting. If a planet is going round a star, then, of course, what's actually happening is that both the planet and the star are orbiting their center of mass, the barycenter. The planet, being much lighter, moves in a big orbit, and the star moves in a small orbit. But very precise spectroscopy is able to measure the change in the velocity of the star. I suppose if you go around in a circular orbit, it'll come towards you a bit and then away. And although this velocity is only a few meters per second, about 10 to the minus 8 to the speed of light, it can be measured. And here's an example of the Doppler effect in the starlight, and this is a sine wave which indicates a planet in a circular orbit. And so by this technique, you can, of course, infer the orbital period and the mass of a planet, and you can also infer if it's eccentric or circular. Now, this technique has led to the discovery of hundreds of planets around other stars, but mainly big planets, planets more like Jupiter and Saturn than like the Earth. That's because a planet like the Earth would induce a motion of only a few centimeters per second in the star it was orbiting, and that's too small a velocity to be detected by this technique. But there's another simple technique which has revealed planets no bigger than the Earth. And this again is very simple. If we are looking at a planetary system and we're looking in the plane of the orbit so that the star transits in front, sorry, the planet transits in front of the star, then we would, if we were looking at the star, observe a slight dimming every time the planet passes in front, because the planet blocks out a bit of the surface of the star. If, for instance, we were looking at a huge distance at the Earth transiting in front of the Sun, then the effect would be very small, 1 part in 10,000, because the Earth has about 1% the diameter of the Sun, therefore 1 part in 10 to the 4th of its area. But this NASA spacecraft carried a telescope which for 3 years pointed at a patch of sky about 7 degrees across and measured the brightness of 150,000 stars in that part of the sky to a precision of 1 part in 100,000, and did that over and over again, once or twice an hour for each star, getting a time series for all these stars. And of course, you then look for cases when you see regular dips. And these regular dips tell you the size of the planet and its orbital period, and many of the planets found this way are indeed roughly the size of the Earth. So we've got every reason to expect that a large proportion of stars have planets around them, some like the Earth. And if you remember that our Milky Way galaxy contains 100 billion stars, then there are probably literally billions of Earth-like planets in our galaxy. And of course, we are especially interested in possible twins of our Earth, planets the size of the Earth at a distance from their star such that water can exist, a temperature such that water doesn't boil away and isn't frozen all the time. And these are planets which we know exist already from Kepler. But we'd really like to observe these planets directly, not just their shadow. And that's very hard. We'd like to be able to get a picture rather like this. And just to imagine what we have to do. Suppose you were an alien astronomer with a big telescope looking at our solar system. Then you'd see the sun looking like an ordinary star. And you'd see the Earth very close to it in the sky, but 1 billion times fainter, looking, in Carl Sagan's nice phrase, like a pale blue dot. And the search is rather like looking for a firefly next to a searchlight. It's very hard indeed to be able to make that detection. And we don't have any instruments that can. But the next generation of telescopes will be able to do just this. This is a picture of the next generation of telescopes which the European Southern Observatory plans to build, and the Americans are planning a slightly smaller one. And this telescope will have a mirror 39 meters across. That's probably nearly 3 times the diameter of this room. Not just one sheet of glass, but a mosaic of hundreds of pieces of glass, all kept by transducers into a perfect figure. And instruments like this will be able to collect enough light to detect the spectrum of a planet orbiting a star and tell us something about what sort of spectrum it has, and therefore clues to what life might be on that planet. Just to indicate what you can, supposing these aliens with a big telescope were looking at the Earth as a pale blue dot, then they could learn quite a bit about it, because the shade of blue will be slightly different depending on whether the Pacific Ocean or the landmass of Asia was facing them. So they could infer that there were continents and oceans, the length of the day, something of the seasons and climate. And by looking at the spectrum of the lights, they could infer that there was oxygen and ozone, etc. And those are the kind of inferences that, using this telescope and others like it, we'll be drawing about Earth-like planets around other stars in 20 years' time. So very exciting developments. Well, the question is, do we expect there to be life on any of these stars, even intelligent life? Well, I think the answer is that we don't really know, because biology is a much more complicated subject than astronomy, and we don't even know how life began on Earth. We don't know what triggered the transition from complex molecules into entities that can metabolize and reproduce, etc. This is an exciting new subject, but we don't understand how life began on Earth, and therefore we can't yet answer questions like how likely is it that it would have started in these other planets, what are the best environments to look in, and how many different possible chemistries are there for life, so how like life on Earth would it be. So we can't rule out 2 options. One is that the universe is teeming with life, and we'll find some evidence for it soon. Or on the other hand, we don't know whether life may be unique to the Earth. And of course, even if simple life were common, then it's not obvious that whether advanced life would be common, because there are many contingencies which have been involved in the various chains of emergence of complexity from simple life to complex life. So we don't know whether Darwin's writ runs through the entire universe, as it were. Of course, if the universe is devoid of very much life, it's disappointing for the searchers, and certainly disappointing for those who look for signals from intelligent life. But on the other hand, it has an upside. It will allow us to be less cosmically modest, in the sense that, tiny though the Earth is in a cosmic context, it might be the only place where advanced life has evolved. And as I'll say at the end of my talk, we should bear in mind that life has a very long future ahead of it. And even if a trivial part of the universe now, it won't always remain so. Just going back to the planets, what surprised people is how much variety the planetary systems display. They're not all like our solar system. Many of them have Jupiter-like planets very close into their star, and some have planets on very eccentric orbits, and one planet has been found orbiting a double star. So if you're on that planet, you'd have two suns in your sky. Incidentally, that planet was found by amateurs who were able, as anyone can, to access some of the time series from the Kepler spacecraft. There's a time series from each star, and they were looking at one, and of course if you have two stars being transited by a planet, then the periodicity is more complicated. This was missed by the automatic program found by amateurs. So it's wonderful that amateurs can now participate in exciting science in this way. Well, the properties of these planetary systems were surprising, but it didn't actually surprise anyone, really, that planets were found around most stars. That's because we had some idea about how stars formed. They form in places like this, gaseous nebular clouds, where a cloud contracts under gravity. And this cartoon shows the different stages. A cloud of gas in the galaxy contracts under gravity, and if it's got even a slight angular momentum, then as it contracts, it will spin faster, like the ballerina pulling in her arms and spinning faster, and will end up with a protostar surrounded by a dusty disk, which spun off the angular momentum. And in that dusty disk, the dust will agglomerate into rocks and then into planets. And we expect this is a generic process. So we're not surprised that planets of some kind form around most stars, because most stars form like this. And incidentally, we can see in the infrared some stars in the process of forming. And I now want to say a bit about stars, because this is related to the question of where the basic stuff that makes the planets comes from. This is another digression about Newton. This is a quote from Newton's Optics. He, of course, explained why the planets move in elliptical orbits. That was his famous result. But he was perplexed as to why the planets in our solar system were all in the same plane, what we call the ecliptic, whereas the comets come in all directions. He thought that was providence. Now, the argument I've just given explains quite naturally why the planets are mainly in a disk. And that's an example of how the advance in science has been able to push back the causal chain. We can now understand why planets form and why they are in a plane, which Newton couldn't understand. And as I'm going to describe now briefly, we can trace the causal chain back to the formation of stars, formation of the first galaxies, even to the formation of the first atoms. Stars are forming in places like this. This is what's called the Eagle Nebula, a huge cloud of dusty gas, about 7,000 light years away. And we see stars dying. There's a whole population of stars forming and dying. And in about 5 billion years, the sun will look like this. It'll blow off its outer layers, leave behind a dense remnant. Here's another star dying. And here's another star dying in a rather messy way. This is a star dying when the star was much bigger than the sun, a star weighing about 10 times as much. And it died as a supernova. And this is a famous object in the sky called the Crab Nebula, which is the expanding debris from a supernova explosion, an explosion witnessed by Chinese astronomers in the year 1054 AD. And this is the record. I can't read this, but perhaps some people can, but I'm told this shows the records produced by the Emperor's court astronomer, I guess their counterpart of the Astronomer Royal, who said that a guest star had appeared, brighter than the moon, and faded away after a few weeks. And at that place in the sky, we now see this object, the Crab Nebula. Well, explosions like this might seem far away and long ago and irrelevant to us. But if it wasn't for these supernovae, we wouldn't be here. Indeed, the atoms we're made of wouldn't be here. The first person to realize this was Fred Hoyle, a professor in Cambridge, who in particular worked with 3 other people. There they are. This is Professor Willie Fowler and Geoffrey and Margaret Burbidge, the 4 people. And they did classic work in the late 1950s about how all the chemical elements of the periodic table could be made in stars. The basic idea is that if you were to take a slice through a big star when it was nearly at the end of its life, it would have this onion skin structure. Remember, stars derive their energy by nuclear fusion. They turn hydrogen to helium, then helium into carbon, and carbon into oxygen, and so on. So inside a star, you have an onion skin where the hotter layers are cooked further up the periodic table. And when the star runs out of nuclear fuel completely, all this stuff is blown out to make the supernova. And this debris will eventually diffuse and merge with the interstellar gas, and then new stars will form from it. So the wonderful story is that all the atoms we're made of were made inside stars, which lived and died more than 4.5 billion years ago, before our solar system formed. We are literally the ashes of long-dead stars, or if you're less romantic, we are the nuclear waste from the fuel that made stars shine. And indeed, inside each of us, there are atoms of carbon and oxygen that came from many hundreds of different stars all over the Milky Way. And so we are linked to the stars really far more intimately than even the astrologers thought. And our galaxy, the Milky Way, is really like an ecological system where pristine gas, just hydrogen and helium to start with, goes into stars, and the small stars burn very slowly, they're still around. The big stars have short lives, and they blow the stuff out, and then it's recycled. So there's a complicated sort of ecological process going on in every galaxy. And this is the kind of thing which Hoyle and his collaborators were the first people to work out. Well, I'm now going to expand horizons a bit. If we could get 2 million light years away from where we are now and look back at our galaxy, it would look like this. This is, as you probably know, the Andromeda galaxy, our nearest big neighbor in space. It's a spinning disk. It's a circular disk viewed almost edge-on, viewed obliquely, and in this disk there are 100 billion stars orbiting around some central hub, in which lurks, incidentally, a big black hole. And our galaxy is like that, and we are out towards the edge. And galaxies like this are the main ingredients of the large-scale cosmic scene. That's one of the nearest ones. Here's another one, which is being viewed more or less edge-on. It's called the Whirlpool Galaxy. And this just shows a survey where every little dot is a galaxy, which shows that in certain sector of the sky, you can literally measure thousands and thousands of them. Now, how do astronomers learn anything about what galaxies are made of? You might think we're completely helpless because we can't do experiments on galaxies or even stars, and galaxies are so big that they change very slowly in general. It takes the sun 200 million years to orbit around the galaxy. But we are saved by computers because we can, in the virtual world of our computer, do simulations. And we can ask a question, what would happen if we crash 2 galaxies together? Of course, particle physicists at CERN, the LHC, they do crash particles together and see what happens. We can only crash galaxies together in the virtual world of our computer. And here's what we see. This is an example of 2 galaxies, and this is computing what gravity does to all the stars when you crash them together. You get a sort of train wreck, and eventually these 2 disk galaxies will merge into one big amorphous galaxy. And we can then look in the sky, and we see galaxies of all kinds, some like this one here. This is a real picture of 2 galaxies in the sky. And having done simulations like the one I just showed you, you can probably convince yourself that what's happened here is 2 galaxies got dangerously close. One is pulling out a tidal plume on the other, and if we came back in 100 million years, these would have merged together. And by doing these calculations, we can indeed get quite a good feel, comparing with a lot of data, for what galaxies are made of, mixture of stars, gas, and other matter, etc., and how they evolve. And we have another advantage, actually, over, say, geologists, in that we can not merely see fossils of the past, we can observe the past. We can do that because we can look at objects a long way away. This amazing picture shows a tiny patch of sky. It would take 50 patches like this to cover the full moon in the sky. And this would look entirely blank with a normal telescope. But seen with a very big telescope, in this tiny area of sky, there are hundreds of smudges. Each of those is a galaxy, many of them fully the equal of our own galaxy, looking so small and faint because of their distance. And some of these galaxies are so far away that their light set out 10 or 11 billion years ago, long before our solar system formed. And so what we can do in astronomy, despite not being able to make do experiments, is we can look at what the universe was like 1 billion, 2 billion, 3 billion, 4 billion years ago, and see if we can understand how the galaxies have evolved. Oh, and I should have given a warning early when I showed that collision, that the Andromeda galaxy is going to crash in our galaxy, just as in that picture, in 4 billion years. It's important to say billion, not million, otherwise people get worried. Yeah. Mm-hmm. Well, we can look out a long way, but we would like to look still further. And of course, the further out we look, the further back into the past we're looking. And we will look back to a time before any galaxies formed. And though I don't have time to go into it, we have, through various techniques, formulated a time chart for how our universe evolved, from a hot, dense state, expanding and cooling. And the various stages are, after 1 second, the universe was at a temperature where nuclear reactions happened, hydrogen and helium are made, and then it cools down, and after about 500,000 years, it cools down to 3,000 degrees, and all the gas becomes neutral, the universe becomes transparent, and we think the first stars and galaxies formed after about 200 million years, when the universe was about 2% of its present age. And there's various lines of evidence, which I can't go into now, which allow us to take seriously this idea. Indeed, I would claim that we can extrapolate the universe back with confidence to when it was about a nanosecond old. I say a nanosecond because that's the time when everything was squeezed so hot and dense that each particle had as much energy as could be produced in the accelerator at CERN. So we understand something about the physics after the first nanosecond. But before the first nanosecond, all bets are off because we don't understand the relevant physics. Now, when people are told that our universe started off in this hot, dense, amorphous state, they tend to ask, does this mean that there's some thermodynamic problem? Because they're used to the idea that the second law of thermodynamics says that structure gets washed out as the universe expands, and it seems that our universe has developed structure. How can that have happened? Well, the answer to that question is that it depends on gravity. Gravity has unusual thermodynamic properties. An object held together by gravity has negative specific heat. If you took the sun, which is held together by gravity, and switched off the nuclear furnace in its center, it would deflate. But after deflation, its center will be even hotter than before to supply bigger pressure. And in the expanding universe, if you have even a tiny fluctuation, then the fluctuation grows as the universe expands. A slight overdensity gives you extra gravity, extra deceleration, so density contrast grows. And I'm going to show you a movie which shows a patch of the universe being simulated and the expansion subtracted out. And you will see the contrast growing as time goes on, which is the region slightly overdense is going to get more overdense as time goes on. And one could do calculations like this and show how structures can evolve even though the early universe is smooth. And this is another picture where a sector of the universe is studied, and in this case the gas and the so-called dark matter are treated separately. And the blue is the dark matter, which is clustering, and then you'll see the gas lighting up into stars. That's the red here. And so this is the kind of picture, and this is a real very elaborate computer simulation of how galaxies form from amorphous beginnings. So a universe that's almost smooth to start with, as it expands, generates enhanced density contrasts, and eventually objects are condensed out to make galaxies. And moreover, we have confidence in this picture for another reason. This is the European Space Agency's Planck spacecraft, which has been observing the background radiation left over from the Big Bang over the whole sky. And it's made a map of the whole sky, and this just is an indication that the sky is not completely uniform. The temperature is about 3 degrees, but there's some places that are warmer by 1 part in 100,000, some cooler by 1 part in 100,000. And this sky, and the warm ones are shown as blue, the other ones as red. And what is encouraging is that if you do one of those simulations like I showed, you don't put in the initial fluctuations at random. You put them in to fit this picture. And then you run the computer forward. And what you end up with is something which is like our present universe. And I won't have time to go into it, but this shows a graph of the density contrast as a function of scale in the universe. The universe goes smooth on average on large scale, and the solid curve is what you predict if the fluctuations initially had that form. The only thing that you should be impressed by is that all the lines which show data telling us the fluctuation amplitude on different scales, they fit onto it. So we have good reason to believe in this so-called hot Big Bang theory, according to which the universe expanded from a hot, dense state that was very smooth and developed fluctuations. And we can highlight a few key steps along the way. Protons and neutrons combine in the first 3 minutes to make deuterium and helium, but no further elements of the periodic table are made. All the rest are made in stars. Then everything expands, cools and dilutes until the gas becomes neutral and transparent, and then the universe enters a literal dark age. The primordial light has shifted into the infrared as the wavelengths have been stretched, and no stars have formed. But then, after about 100 million years, the first stars form, as in that movie, and heat the universe up again. And the stars then assemble into galaxies. And processes within those stars then synthesize the periodic table, especially the short-lived stars with high mass. And then the second generation stars form from gas contaminated by the ejecta from the first generation, and our sun was one of those. And so this indicates the stages in the emergence of complexity. Now, crucial to this process is gravity, as I said. And I'm going to show, this is my only technical slide, but it's one of my favorite pedagogical slides, so I'll just spend a moment on it. What this shows is upwards, it shows mass, and along the horizontal line, it shows radius. And it shows at the bottom a proton, and it shows the horizontal line, the line of slope 1 at the top is a black hole line. And solid objects are on the line of atomic density. Sugar lumps, people, asteroids, etc. And as the mass goes up, then for objects of given density, the radius goes to the cube root of the mass, so you're getting closer to the black hole line, so gravity is becoming more important. And if you try to assemble an object bigger than an asteroid, then gravity makes it round. If you assemble an object bigger than Jupiter, gravity crushes it. It turns into a star. And this simple picture indicates the scale of the physics of stars. And the one point I want to emphasize is that the scale is very, very compressed. You see 10 to the 19, 10 to the 38, 10 to the 57. And the reason for that is that gravity is very weak on the microscopic scale. If you take two, a proton and electron in a hydrogen atom, then the electric forces between them are 38 powers of 10 stronger than the gravitational force. So gravity is very, very weak. But electric charges are positive and negative, so in a big object they cancel out, whereas everything has, as it were, the same sign of gravitational charge. So gravity always wins. But it's because gravity is so weak that objects have to get very big before gravity becomes important. And we wouldn't exist if gravity wasn't weak, because if gravity was, say, only 20 powers of 10, rather than nearly 40 powers of 10 weaker than electric forces, then objects as big as us would be crushed by gravity, and we could have a small-scale speeded up universe. So it's the fact that gravity is so weak that gives us so many powers of 10 between the microscopic scale and the cosmic scale. And so if we were to list the prerequisites for our complex cosmos, then there are various stages. First, as I've explained, gravity is crucial in allowing density contrast to grow in the early universe and allowing stars to hang together. But as I said, the weaker it is, the better. And so this number, the ratio of the electric and the gravitational forces between two protons, is a very, very big number. If that wasn't so big, then we wouldn't have a universe with long life and large objects. Just some other requirements. The universe must deviate from thermodynamic equilibrium in order for complexity to evolve. And that means, for instance, that it wouldn't be any good if the universe expanded for 100,000 years and then recollapsed, because then it would always be in a fireball state. So you've got to have non-equilibrium thermodynamics so that life can exist, and of course we exist because we absorb high-grade energy from the sun and radiate it into the cold of intergalactic space where the temperature is 3 degrees Kelvin. We also need matter-antimatter asymmetry, because in the very early Big Bang, there are equal amounts of lots of matter and antimatter. And so if there were equal amounts, then as it cooled down, they'd all annihilate, and we'd have lots of radiation, but no atoms. So there's got to be some favoritism of matter over antimatter in the early universe. And also, there's got to be sort of tuning between two of the basic forces in the microworld. The electric force, which drives the nucleus apart, and the nuclear force, which holds the protons and neutrons together again. If that wasn't in balance, then we wouldn't have a periodic table. And so the famous binding energy picture that you get energy from nuclear fuel depends on a certain balance between those two basic forces of nature. And there need to be stars which form in the universe. So it's got to last long enough for stars to form, because it's in the stars that the periodic table is built up. And for all this to happen, we need to have a sort of tuned expansion rate. If the universe expanded too slowly, it would recollapse too soon. If it expanded so fast, then galaxies couldn't pull themselves together under gravity because the kinetic energy would win. And one does need fluctuations to be present. If there were a completely smooth early universe, then there'd be no galaxies now. The universe would just be cold, neutral hydrogen and helium. So there are these sort of tuning parameters. And just to advertise, I wrote a book some years ago called Just 6 Numbers, which mentions 6 important numbers in the universe, which I've mentioned, which are crucial in determining why the universe allows these various stages in the build-up of complexity, from simple amorphous hydrogen and helium all the way up to chemistry, which can give rise to planets and then life on some of the planets. Well, can we push the causal chain further? I mentioned that since Newton we pushed it back a bit. We understand the stars and galaxies. We can go back to a nanosecond. And the nanosecond, incidentally, is when the entire observable universe would have been squeezed down to the size of our solar system. But if you want to ask fundamental questions like, where did those fluctuations come from? Why is there more matter than antimatter? Why is the universe expanding the way it is? Then all cosmologists agree that we've got to go back much further. Indeed, some think we've got to go back as far as this. And this is one of my favorite magazine covers. We've got to go back to the time when the entire universe was squeezed, not just to the size of our solar system, but to the size of a cricket ball. And before going further, I should put up this hazard sign, because the physics of that very early stage is, of course, conjectural. It's far beyond what we can simulate in the lab. We only have indirect evidence. But many people think, incidentally, that the fluctuations are indeed produced as quantum effects when the universe was of microscopic size. And they then expand and now give rise to the galaxies that are stretched across the sky. If I wanted a logo for my research area, I'd choose this, an Ouroboros. This image is a nice way of depicting the interconnectedness of the microworld on the left and the cosmos on the right. The inner space of atoms and the outer space of the universe. And we learn no links between small and large, between left and right. Our complex everyday world of life and mountains is determined by atoms and chemistry. Halfway up there's a link between the nuclei inside atoms and stars, because it's those nuclei that power the stars. And though I haven't had time to mention it, galaxies are held together not just by the gravity of what you see, but by mysterious dark matter particles, which are some sort of subnuclear particles made in the Big Bang. The left-hand side is the domain of the quantum. On the right-hand side, gravity holds sway. And general relativity and quantum theory are the two great pillars of 20th century physics. But they haven't yet been meshed together, as you probably know. There's a search for unified theory. Now, this doesn't matter to most scientists. It doesn't matter because if you're a chemist, you don't worry about the gravitational pull between the atoms in a molecule. Conversely, if you're an astronomer, you don't worry about the quantum fuzziness in the orbits of planets because they're so big and it's negligible. So because of that big number, the domains of relevance of those two are separate. But if you want to understand the very beginning, what banged and why it banged, then we do need a unification, symbolized gastronomically at the top of this picture here, because right back at the beginning, the universe was so dense that, as it were, quantum fluctuation could shake the entire universe. And so we won't understand the very early universe and why it's expanding the way it is and why it's set up the way it is until we have this unified theory, unifying the very large and the very small, which are two separate great frontiers of physics. But before leaving this diagram, I want to emphasize that there is a third frontier, neither the very small nor the very large, but the very complex, the things at the bottom, like us, insects, people, and mountains. And incidentally, we ourselves are midway on a log scale between atoms and stars. We're large enough, compared to atoms, to have layer upon layer of intrinsic structure, but not so large that we're crushed by gravity. In fact, the geometric mean of the mass of a proton and the mass of the sun is 50 kilograms, within a factor of 2, I guess, of the mass of each person here. So we are literally midway on the log scale between atoms and stars. So we need to be mindful of the atoms we're made of, but equally of the stars that made those atoms. And this third frontier at the bottom, the frontier of complexity, as I don't need to tell people in this audience, is the most challenging one. Even an insect with its layer upon layer of complexity is harder to understand than a star, where intense heat and compression by gravity precludes any complex internal chemistry. This, incidentally, is the famous flea drawn by Newton's least favorite colleague, Robert Hooke, who was a pioneer experimenter and pioneer microscopist, and he produced a wonderful book called Micrographia in the 1660s, showing things seen under the first microscope, including this, and this must be wonderful for people to first see the intricate detail on an insect. Well, the bedrock nature of space and time and the unifications of the cosmos and the quantum, symbolized at the top of this picture, are surely among science's great open frontiers. But calling this a theory of everything is hubristic and misleading, and that is a phrase used often by some particle physicists. That's because this unification is irrelevant to 99% of scientists. The problems in biology and in environmental and human sciences, they remain unsolved because it's hard to elucidate their complexities, not because we don't understand subatomic physics well enough. It would make no difference at all to these problems whether we have that fundamental theory. The sciences are sometimes likened to different levels of a tall building. Particle physics in the ground floor, then the rest of physics, then chemistry, all the way up to psychology, and the economists up in the penthouse, of course. Mm-hmm. And there's a corresponding hierarchy of complexity: atoms, molecules, cells, organisms, and so forth. But the analogy with the building is poor. In a building, insecure foundations imperil what's above, whereas the higher level sciences dealing with complex systems aren't imperiled by insecurity in fundamental physics, because each level in science has its own autonomous concepts and theories. I suppose nearly all scientists are reductionists insofar as they assume that everything, however complicated, obeys the basic laws of microphysics, Schrödinger's equation. But that type of explanation isn't what we want. Even a phenomenon as unmysterious as the flow of water in pipes or rivers is studied in terms of emergent concepts like viscosity, turbulence, and so forth. Specialists in fluid mechanics treat the water as a continuum. They don't care that it's actually made up of H2O. And even if we had a hypercomputer that could solve Schrödinger's equations for the flow, atom by atom, then the resultant simulation wouldn't provide any insight into why waves break or what makes a flow go turbulent. And of course, new irreducible concepts are even more crucial to our understanding of really complicated phenomena. And as I said, even the smallest insects embody intricate structures that render them mysterious, and when we grapple with the human scale, then a holistic approach proves more helpful than naive reductionism. Animal behavior makes the most sense when understood in terms of goals and survival, and we can predict with confidence that an albatross will return to its nesting place after wandering thousands of miles in the Southern Ocean, but such a prediction would be impossible, not just in practice, but even in principle, if you considered the albatross as an assemblage of electrons, protons, and neutrons. So phenomena with different levels of complexity are understood in terms of different irreducible concepts: turbulence, survival, alertness, and so forth. The brain is an assemblage of cells, a painting is an assemblage of chemical pigments, but in both cases, what's important is the pattern and the structure, the emergent complexity. By the way, when we think about the progress and limits of science, I think we should be open-minded about the possibility that some fundamental truths about nature may be too complex for unaided human brains to ever comprehend. They might elude us simply because they're beyond human brains, just as surely as quantum theory is beyond a chimpanzee. So I think we should accept that we may hit the buffers in some stages. I should say, when I said this in an earlier talk, I was contested by David Deutsch, a distinguished theoretical physicist who pioneered key concepts of quantum computing. He pointed out that anything was in principle computable, but that's not the same as having insight. To give a simple example, if you know coordinate geometry, and I say, imagine the shape x squared plus y squared less than 1, you can think of that as a circle. If I give you the algorithm for the Mandelbrot set, I think no human being can envisage that in the same way. So in the same sense, we can compute many things, but we won't have insight into them. So that's what I meant in saying that there may be some things that we'll never have adequate insight into. Now, I want to turn now back to the Earth. I'm sometimes asked, does astronomy give any particular perspective on terrestrial problems? And I would answer that I think it does. Here's the rather crude time chart of biological evolution, and I think unless you live in parts of the Muslim world or in Kansas and Kentucky, you're all happy with that. But the point I want to make is that most people familiar with Darwinian evolution tend to think that we are in some sense the culmination of it. It's all led to us. But no astronomer could believe that. Because one thing we know is that our sun is halfway through its life. This is a sort of crude time-lapse picture. It'll be the sun's been going 4.5 billion years. It'll be another 5 billion before it flares up and dies, engulfing the inner planets, vaporizing any life on Earth. So our sun has a long future, and the universe perhaps even longer, perhaps forever. And as Woody Allen said, eternity is very long, especially towards the end. So what this tells us is that post-human evolution, here on Earth and far beyond, could be as prolonged as the Darwinian evolution has led to us, and even more wonderful. Darwin himself recognized that future species will be different from those on Earth. But I think we would now strengthen Darwin's statement, because in future the changes will be faster. They were determined, or at least modulated, by conscious choices of intelligent beings, rather than being the outcome of Darwinian selection. Indeed, machines may take over quite soon. And I mentioned already that if there are communities living away from the Earth, then they may modify themselves and produce post-humans within a few centuries. So any creatures witnessing the sun's demise a few billion years from now and sending this postcard won't be humans. They'll be as different from us as we are from a bug, or probably more so. Well, time won't allow me to develop these speculations further, because I want now to focus back on the here and now. And let me do this via a cosmic vignette. We've had these images for 40 years. They're iconic for environmentalists. But supposing that the hypothetical aliens who I invoked earlier, looking at the Earth as a pale blue dot, suppose they'd been looking at this picture for our entire planet's history, what would they have seen? Well, over nearly all that immense time of 4.5 billion years, Earth's appearance would have altered very gradually. The continents drifted, the ice cover waxed and waned, successive species emerged, evolved, and became extinct. But in just a tiny sliver of the Earth's history, the last 1/1,000,000th part, just a few thousand years, the patterns of vegetation would alter much faster than before. This signaled the start of agriculture as human populations rose. And then there were other changes, even more abrupt. Within 50 years, little more than 1/100th of 1/1,000,000th of the Earth's age, the carbon dioxide concentration in the Earth started to rise anomalously fast, and something else unprecedented happened. Rockets launched from the planet's surface escaped into orbit or went to the planet or the moon. Well, if they understood astrophysics, the aliens could have predicted that our biosphere would face doom in a few billion years when the sun flares up and dies. But could they have predicted this sudden fever halfway through the Earth's life? These human-induced alterations occupying overall less than 1/1,000,000th of the Earth's elapsed lifetime and seemingly occurring with runaway speed. And more important, if the aliens continue to keep watch, what might they witness in the next 100 years? Some years ago, I wrote a short book on this theme, which I entitled Our Final Century, with a question mark. The publishers left out the question mark. And the American publishers changed the title to Our Final Hour. I guess Americans like instant gratification and perhaps the reverse. Well, I conjectured in this book that taking all risks into account, there was a substantial, maybe 50% chance that we wouldn't get through to 2100 without some kind of disastrous setback to our civilization. And just as a plug, I've got a more recent book on this theme called From Here to Infinity. The main theme of my book was that over most of history, the threats to humanity came from nature: disease, earthquakes, floods, and so forth. But this century is special. It's the first when one species, ours, has Earth's future in its hands and could jeopardize life's immense potential. We're deep into a geological era, sometimes called the Anthropocene. The threat of global nuclear annihilation, involving tens of thousands of bombs, hung over us during the Cold War, and that's now in abeyance. But later this century, there could be some new realignment of new superpowers that could be handled less well or less luckily than the Cuba crisis. So a nuclear disaster is certainly still on the list. But that's not the only one. I don't think it's the major one. Devastation could arise insidiously rather than suddenly through unsustainable pressure on energy supplies, food, water, and other natural resources. Indeed, these pressures, which many people here know far more about than I do, are the prime threats without enemies which confront us. They're aggravated by climate change, and they become ever more intractable as the population rises. And regarding population, as we all know, it's now about 7 billion, and nothing barring catastrophe can stop it rising to about 9 billion by mid-century. That's because most people in the world now are young. This is an age histogram contrasting two countries. On the left is Uganda, and on the right is Italy. Italy, the population is stabilizing, even going down. In Uganda, most people are young, and almost certainly the population is going to rise as the histogram on the left becomes more like that on the right. And just for comparison, I found this is the similar one for China, which is somewhere in between, which has stabilized. But by 2050, the projections show there will be 2 plus or minus a half billion extra people, and they will be mainly in India and Africa. And in David Dorling's book, he has this picture which shows the extra populations by 2050, showing where they mainly are, and the bloated bits are primarily India and Africa. That's by 2050, but of course, although we can't change that projection much, we can change projections beyond that, and in benign ways by enhanced women's education and things of that kind. And it's extra motive to encourage such things, because I think everyone would agree that the higher the post-2050 population becomes, the greater will be all pressures on resources, especially if the developing world, where most of the growth will be, narrows its gap with the developed world in per capita consumption of energy and other resources. But ecosystems, of course, are already vulnerable. Humans appropriate about 40% of the world's biomass, and that fraction's rising, and the resultant ecological shock could irreversibly impoverish our biosphere. And the risks are aggravated by climate change. Biodiversity, incidentally, is a crucial component of human well-being. Someone mentioned this morning fish stocks, and we're clearly harmed if they dwindle to extinction. There are plants in the rainforests whose gene pool might be useful to us. But of course, for many environmentalists, these instrumental and anthropocentric arguments aren't the only compelling ones. For them, preserving the richness of our biosphere has value in its own right, over and above what it means to us humans. Climate change, I wasn't going to say much about that, but just a couple of minutes on climate change, my take and what's likely to happen. I personally am skeptical about any move to cut annual CO2 emissions in the next 25 years. The projections show them rising by about 25%. I don't see that changing. But my guess is that 25 years from now, it'll be clear, both from better modeling and also from the longer-term trend of temperature rise that we will then have, whether we are on the steep or the shallow of the IPCC's projections. what the climate sensitivity is. If we're on the shallow one, let people relax and say that on a longer time scale we can convert to clean energy without disaster. But if we're then clearly on the steep one, then I think there'll be pressure for panic measures, including geoengineering. And geoengineering is really a nightmare because the consequences are unpredictable. The only winners from geoengineering will be international lawyers, because if you can blame other people for the weather, then there's unlimited capacity for litigation and disputes. So that's my rather pessimistic prediction. Well, despite those pessimisms, from what I've learnt, feeding 9 billion people is not impossible, and other advances in healthcare and information technology could allow us to feed 9 billion, but beyond that, it might be harder. But there's a downside to the same technologies that promise so much. They open up new vulnerabilities, and this is my final part of my talk. For instance, as we all know, global society depends on elaborate networks, electricity grids, air traffic control, international finance, just-in-time delivery, and so forth. And unless these are highly resilient, then their manifest benefits could be outweighed by catastrophic, albeit rare, breakdowns cascading through the system. Pandemics can spread at the speed of jet aircraft, causing maximal havoc in the shambolic but burgeoning megacities of the developing world. Social media can spread psychic contagion, rumors and panic, literally at the speed of light. These are all real-world analogues of what happened in 2008 in the financial system. And incidentally, it's interesting that Bob May analyzed with Haldane the financial system using the same mathematics he'd used in his famous earlier work on multi-species ecologies to show that multi-species ecologies aren't necessarily more stable. Well, these threats all impel us to plan internationally, of course. Take one example. Whether a pandemic gets global grip or not may depend on how quickly a Vietnamese farmer identifies some strange disease in his animals. And many of them, energy and climate change, for instance, involve multi-decade timescales, plainly far outside the comfort zone of most politicians. And of course, this is an issue that perhaps leads us to think about the need for new international organizations. But I think another concern is this. Because of technology getting more powerful, malign or foolhardy individuals or small groups have far more power and leverage than in the past. Concern about cyber attacks by criminals or by hostile nations is rising sharply, and advances in synthetic biology, likewise, offer huge potential for medicine and agriculture, but they amplify the risk of bio-error or bioterror. Just 18 months ago, you may remember 2 research groups, one in Holland, one in the US, showed that it was surprisingly easy to make an influenza virus both more virulent and more transmissible, and they were pressured to redact some details of their publication. And that's a portent of issues that are going to become more acute. So, in our more interconnected world, where technology empowers us more than ever, we are vulnerable not just to the old risks like nuclear risks, but to new kinds, events of seemingly low probability, but of such catastrophic consequences that their reduction should be high on the agenda. IT and biotech are exciting and in many ways benign, but they have a dark side because they present new threats, more diverse and more intractable than nuclear weapons did. That's because the technology and expertise for bio and cyber attacks will be accessible to millions. They don't require large special purpose facilities like making H-bombs. Cyber sabotage effects like Stuxnet and frequent hacking of financial institutions already put these up the agenda. Those of us with cushioned lives in the developed world fret a lot about minor hazards, improbable air crashes, carcinogens in food, low radiation doses, etc. But I think we're less secure than we realize. We and our political masters are almost in denial about scenarios that haven't yet happened, thankfully, but which could arise as unexpectedly as the 2008 financial crisis, and could cause worldwide disruption. Society could be dealt shattering blows by misapplication of technologies that exist already. And we're kidding ourselves, incidentally, if we think that those with technical expertise will all be balanced and cautious. Expertise can be allied with fanaticism, not just a tradition of fundamentalism that we're mindful of today, but that exemplified by some New Age cults, extreme eco-freaks, etc. The global village will have its village idiots, and they will have a global range. Think, for instance, of an extreme eco-freak who thinks there are too many human beings in the world, who gets empowered by the latest synthetic biology. That's the sort of thing I worry about. So I think there needs to be a serious effort involving natural and social scientists to compile a more complete register of these extreme risks and to enhance resilience against the more credible ones. But what about the more distant future? We can predict confidently that 50 years from now, the world will be warmer and more crowded. But we can't predict how our lives might then have been changed by transformative technology. As we heard this morning, some of these technologies develop very fast. The smartphone, internet, and their ancillaries would have seemed magic 25 years ago. Will people want to go into space? I mentioned already that some pioneers might, and this might be a step towards divergence into a new species. But don't expect mass emigration from the Earth. That'll never happen. Nowhere in the solar system offers an environment even as clement as the Antarctic or the top of Everest. So space doesn't offer any escape from the Earth's problems. And so all these problems I'm mentioning have to be solved here. Well, as regards looking 50 years ahead, I'm cautious because one of my predecessors as Astronomer Royal said in the 1950s that space travel was utter bilge. He was proved wrong fairly quickly, and so I'm not going to make any predictions. But of course there are techno-evangelists like Ray Kurzweil who predict that intelligent machines will take over within 50 years. He talks about the so-called singularity. He incidentally, I read a profile of him recently, he thinks he's going to live forever because he'll be able to download his brain into a computer, and he's taking 150 pills a day now to keep going for the next 20 years until this technology comes online, and he's also paid to have his body buried. His body frozen, the so-called cryonic method, so that he can be revived when the technique advances. Incidentally, regarding cryonics, I was interviewed by a group of these people in California who offer to freeze your body, and I upset them all by saying I'd rather end my days in an English churchyard than a Californian refrigerator. And they call me a deathist, which is a sort of insult for them, of being very old-fashioned. Yes. Well, anyway, despite Kurzweil, it is fairly clear that there are going to be rapid advances, and some may remain the stuff of science fiction for longer, but nonetheless, by the end of this century, our society and its economy will have been deeply changed by things like autonomous robots and maybe intelligent robots. Although we might hope that they will be sort of idiot savants rather than people, rather than creatures that develop a mind of their own. Well, I've mentioned the downsides of advancing technologies, and some might dismiss what I've said as an exaggerated Jeremiad. After all, human societies have survived for millennia, despite storms, earthquakes, and pestilence. But I think it's different now, because the human-induced threats that I've mentioned are only newly emergent. So we don't have a time base to show we can survive them. We can't be sanguine that we would survive them for long. Still less can we be confident that we would survive the downsides of technology that may emerge in the next 50 years. And I think we've got to accept that technological advances bring with them great hopes, but also great fears. And just a final point which is addressed more to the students here, which is that now that the impact of these researches can be much greater, I think scientists have a much deeper responsibility to engage with society. Politicians need the best in-house advice, but more than that, choices on how technology should be applied so that we can derive the benefits and minimize the risks should not be choices made by scientists alone. They require wide public debate. And that debate must be leveraged by scientific citizens who will engage from different political perspectives with the media and with the public, which is attuned to the scope and limits of science. And we shouldn't be bashful as scientists in proclaiming that despite the challenges, there seems no scientific impediment to achieving a sustainable world where all enjoy a lifestyle better than we in developed countries do today. We can, I think, truly be techno-optimists. But the intractable politics and sociology, the gap between potentialities and what actually happens, certainly engenders pessimism. Politicians look to their own voters in the next election. Stockholders expect payoff in the short run. Medical research focuses on diseases of the rich, not enough on tropical diseases. We need a change in priorities and perspective, and soon, if we are to stem these long-term risks of environmental degradation, to prioritize clean energy and sustainable agriculture, and to handle the Promethean challenge of new, even more powerful technology. Problems caused by shortages of food, water resources, and the transition to sustainable low-carbon energy can't be solved quickly, nor by each nation separately. And so that's why we clearly need to think in a more international way. We need to realize that we are all on this crowded earth together. We know that we are stewards of a precious pale blue dot in the cosmos, a planet with a future measured in billions of years, whose fate depends on humanity's collective actions. And we should be mindful of that. And I give the final word to a scientific sage, the great immunologist Peter Medawar. And he said, I quote, "The bells that toll for mankind are like the bells of alpine cattle. They're attached to our own necks. And it must be our fault if they do not make a tuneful and melodious sound." Thank you very much.
Thank you, Martin, for this great journey from the Earth to the solar system, to the galaxies, to the early beginning of the cosmos, and then back to the Earth and to our probable end. I'm sure there are some questions. We will have not much time, but I don't know how this works, but anybody who has a question on any part of the things or a comment that Martin Rees raised. Yes. Can the lights be raised a little bit? Because can you see the question?
Yes, I can.
Professor Rees, thank you very much. I wanted to ask you a little bit more specifically about geoengineering. I know there's a highly influential 2009 Royal Society report that talked about the necessity of research, and yet what I thought I heard you saying was that even if we're at a point, not at deployment, but we're seriously considering the capacity and capability, that you see it as a non-starter. So do you feel that that's been a shift in looking at whether it's carbon removal or solar radiation management, that it's a no-go from your perspective?
Well, I mean, as you indicate, there are two kinds of geoengineering. The one kind is to build as it were, artificial trees to suck out of the atmosphere the CO2 that we put in there. This is benign, because it's essentially undoing the geoengineering we've done already. But at present, as you know, this isn't feasible. It would need huge expense and a huge amount of power. If that could be developed, that would be great. But the kind that involves putting some sort of dust in the upper atmosphere, artificial volcanoes, etc., it might be the lesser evil if things get really bad. But the problems are, of course, that we'd need to have a really good climatic model to understand the consequences of doing this. We'd have to understand the climate very well. And also, it's only a way of buying time, because you've got to keep on doing it. If you stop, then within 10 years, the atmosphere is transparent again, and you get sudden warming. And of course, the other downside is that ocean acidification, which is the consequence of the rising CO2, would proceed unabated. So it would be very unfortunate if a belief that geoengineering was a panacea were to reduce the motivation to cut CO2 emissions. So I think, nonetheless, that we should do research into these options, simply to convince people, if it's the case, that it isn't a very acceptable option. Yeah.
I'm one of those village idiots who's trying to figure out your understanding of the cosmos. You seem to be saying a very fundamental moral message, that the current science and paradigm is actually enabling the rich to escape the fate that you said, but have abandoned the majority. Is that a moral message that you're saying that we are right under?
No, I really meant to say the opposite, saying that there's nowhere away from the Earth which is even as comfortable as the North Pole, etc. So I mean, I think that the only humans who will go into space will be crazy adventurers like those who climb Everest, who will want to explore, and a group of pioneers may want to set up. But I think it would be indeed very dangerous, and I certainly was not saying this at all, to believe that we can solve our problems by evacuating the Earth. We can't at all. I think the future of space is going to be just a few pioneers, but they will, after a few centuries, become very alien to us because they will evolve into different species. And I suppose we should wish them luck in doing that, and also perhaps be slightly grateful if they're out there, because if you take the worst possible disaster that would wipe out all humans on Earth, then there would be something out there that was sort of at least quasi-human that could carry the torch forward over the next few billion years. But I certainly wasn't saying that there was a comfortable escape for the privileged at all.
Well, Martin, thank you very much. It's very exciting. Now, coming back to my learned friend question, I think in regards to the totality of your reservation about those who have second thought or reverse engineering. Now, the point is, I think that here, how do you rationalize with your principle that to say that, that the the absence of evidence is not the evidence of absence? So how do you correlate with the perception that you have foundation-wise?
You talk about life in space?
That's right.
Yes. Well, I try to be open-minded. I mean, my line is that we know too little about how life evolved even on Earth to be able to say whether it's likely or unlikely. So I think we should be entirely open-minded. I mean, it's true that we haven't found any evidence for it, but we wouldn't expect to find evidence easily. So I think if you ask most experts, they would be very surprised if there was no life of any kind. As regards intelligent life, then, of course, we should be more open-minded. Of course, there are some people, as you know, searching for signals from life. And, of course, I should mention that I get letters from people who know the answer already. I get letters from people who've met the aliens, they've been abducted by them, etc. And I say two things to these people. The first thing is, do you really think that if the aliens had made the huge effort to come across interstellar space here, would they just meet a few cranks, make a few corn circles, and then go away again? It seems unlikely. And the second thing I tell these people is to write to each other and not to me. Yeah.
Okay, one more question. Peter.
So thanks for a great talk. So we've come a long way understanding our universe, and you gave excellent examples. But there's a kind of a sobering thought that we missed out all this dark energy and dark matter, which accounts for like 70% of what is out there, which is like, describing the Earth without taking into account the oceans. So can you comment on that a bit about your feeling of what we might have missed at all, or maybe something about why we missed this important part?
Well, I mean, the dark matter we haven't missed. We've got very, very strong grounds for believing that there's 5 times as much mass in dark particles as in luminous particles. This shouldn't surprise anyone. Not everything on the Earth shines. There's no reason why everything in space should shine. We don't know what they are. We know these are uncharged particles that have a small cross-section of interacting. And indeed, we couldn't understand galaxies as they are now, nor how they evolved without it. So we know quite a lot about the dark matter, and it must be there. The so-called dark energy, I should say, this is a surprising effect which is causing the expansion of the universe to accelerate, not decelerate. It means that even empty space exerts a force which is completely unimportant on Earth, even in the galaxy, but on the cosmic scale, it overwhelms gravity and gives a push which outweighs the gravitational deceleration. And this is actually, it's not important in any astrophysical context. It doesn't change anything, really, because it's not important in galaxies, not important in the early universe. But it is a challenge to physicists because, as I mentioned, the big challenge of 21st century physics is to reconcile or unify the force of gravity, which is related to space and time in Einstein's theory, and the microworld of quantum theory. This hasn't been done, but most people suspect that that unification will require understanding the structure of space on a scale of 10 to the minus 33 centimeters. That was, in fact, the left-hand part on that the diagram I showed you. That's where quantum theory and gravity meet. Just as I can't break up this lectern into pieces smaller than atoms, then it's believed that you can't break up space or time into quanta smaller than that. But that quantum of space is a billion times smaller than atoms. So it's a long way from any direct experiment. But it's suspected that if you could look at space on that scale, you'd find that what we think of as a point in space is actually a tightly wrapped origami in extra dimensions in a very complicated way. And we're very far, as you probably know, from having a theory. String theorists are working hard on it, but we don't know if they're on the right lines even. When we have such a theory, then one of the things it's got to explain is why even empty space has this tiny amount of energy in it. That is a big challenge. And the dark matter, we understand its key properties, and I think we will find out exactly what it is, either by accelerated experiments, or by seeing annihilation effects, or by detecting the particles in underground experiments. So I think we're making a lot of progress there. But the dark energy, fortunately, doesn't affect anything else I said. But that's a big challenge.